Hi students, welcome back to another lesson in pre-calc. Today we're going to be taking a look at lesson 4.2, but we're going to be looking at this lesson through the lens of special right triangles and the unit circle. So this will be your introduction to the unit circle and how the unit circle connects to two special right triangles you learned in geometry. Let's get started. So as we move through this, I want to remind you that we will continue to work with our trig function relationships of opposite over hypotenuse for sine, adjacent over hypotenuse for cosine, opposite over adjacent for tangent, as well as each of their reciprocal identities. So let's go ahead and move into learning a little bit more about the unit circle. Unit circle, it gets its name because we mark that the radius of the unit circle is a distance or length of 1. This is a really interesting idea because it simplifies a lot of the process. So let me go ahead and impose just an XY plane. So when we're working with this unit circle, we're going to have its origin or center be in the middle of the circle, okay? And from there, what we can do is we start to see that we have coordinates, assuming that we have that radius of 1. For example, the coordinate of this spot on the unit circle would be 1, 0. And the coordinate of this would be 0, 1. Here, we're at -1, 0. And down here, we're at 0, -1. Because we're using this idea of a unit being the radius, it allows for us to start to develop measurements around the circle. For example, I might have a measurement here or a measurement here, okay? So as we move forward, I want you to keep this image in your mind as well as handy in your notes. Let's take a look at the next connection. So as we said, we labeled different coordinates around our unit circle. For example, we said this coordinate would be 1, 0. We can use this same idea and extend it if we have any angle measure. The horizontal distance from the origin out is the x coordinate in an ordered pair, and the vertical distance up is the y coordinate of your ordered pair. Now, by labeling the hypotenuse of our triangle as 1 or our unit circle, we're going to go ahead and calculate our cosine, sine, and tangent values. So recall cosine is the adjacent side over the hypotenuse. In this case, that would be x over 1. Well, x over 1 is the same thing as just x. What this tells us is that the horizontal distance from the origin out is the same as taking cosine of whatever angle measurement you are trying to calculate. Or it's another way of saying the x coordinate is cosine of your angle measure. Let's do the same process with sine. Sine of theta would be opposite over hypotenuse. So y over 1. Or sine of theta is just y. In this picture, that means that if I take sine of my angle measure, I'm going to calculate the vertical distance up or the vertical distance to the edge of my circle. Right, let's go ahead and do the last calculation. Tangent is opposite over adjacent, so y over x. So if I want to find the tangent value of any angle measure on our unit circle, I can take the y coordinate divided by the x coordinate, or the sine value divided by the cosine value, because sine is y and cosine is x. Again, this concept of recognizing that the x coordinate goes with cosine and the y coordinate goes with sine is very important and is going to continue to carry through So don't forget that one. I like to remember it as alphabetically C comes before S and alphabetically X comes before Y. So just a nice little trick for you. All right, so now we have this idea of a unit circle is a circle with a radius of 1. And we understand that if I put a triangle in centered at the origin, it's going to create different coordinates around the outside edge of the circle. So what triangles do we care about? Well, there are two special triangles we learned in geometry. The first is a triangle with an angle measure of 45 degrees. Recall that if I have an angle measure of 45 degrees, I've created an isosceles triangle. That means the two legs are going to be congruent. Now, in true fashion of wanting to keep this connection with our unit circle, we're also going to label the hypotenuse as being 1. So if I want to find out what each of these are going to be, I would need to calculate out the leg measurements of this triangle. To do that, I'm going to use an arbitrary value of x and the Pythagorean theorem, which says my legs squared combine to equal my hypotenuse squared, or a squared plus b squared equals c squared. Working through this and solving this for x, I would get 2x squared equals 1. Dividing both sides by 2, I get x squared equals 1/2. And last but not least, taking the square root of both sides, I end up needing to do a little bit of work with radicals. So we get x equals the square root of 1/2. Now, if you remember, we can take the square root of the top and bottom number separately. The square root of 1 is 1. The square root of 2, I can't simplify, so I leave it as the square root of 2. However, we also learned that we cannot allow a radical to be in the denominator. So to get rid of the radical in the denominator, we multiply by the number that will create a perfect square. In this case, I'm going to multiply the top and bottom by the square root of 2 over the square root of 2. Remember that by doing this, we're multiplying by the equivalent of 1, and this is going to allow for the top to have the radical, and the square root of 2 times the square root of 2 is just 2. So we've now found that x is equal to the square root of 2 over 2. If we recall, we know that if I want to find the sine value of 45 degrees, I can take and say, this is my angle I'm measuring from. Therefore, the side that is opposite is root 2 over 2, and the hypotenuse is 1. So sine of 45 degrees is just root 2 over 2. This connects perfectly with what we just discovered on the previous slide. The sine value is the vertical distance up. The cosine of 45 is the adjacent over the hypotenuse. In this case, that's root 2 over 2, all divided by 1, or just square root of 2 over 2. Again, aligning perfectly with the idea that the horizontal distance is cosine of our angle measure. Last but not least, we have tangent of 45 degrees. Tangent is opposite over adjacent. The same thing divided by the same thing is 1. If I take that sine divided by cosine, I also confirm that I get 1 out. Okay. We're going to take and utilize these measurements in a future slide. So for now, let's pause and evaluate the second special triangle we work with. The second special triangle we work with is our 30, 60, 90 triangle. Now, I'm briefly going to go over the idea of where the measurements come from here, but the 30, 60, 90 triangle is derived by using an equilateral triangle. So an equilateral triangle has 3 equal sides as well as 3 equal angles. And what we do from here is we draw in an altitude. The altitude of this triangle is going to bisect the base. When I bisect the base, that makes this part equivalent to this part. It also bisects this upper angle, creating our 30-degree angle, our 60-degree angle, and our 90-degree angle at the base. Now, in keeping with our unit circle concept, I'm going to label that the side of my equilateral triangle is of 1 unit because we want to align it with the unit circle. I also know that this base side is going to be 1/2 because our altitude bisected the other side. From here, I can write my Pythagorean theorem and solve for the red dotted line or the horizontal line over here. So again, that height is this horizontal side right here. So I would have h squared plus 1/2 squared equals 1 squared. H squared plus 1/4 equals 1. Subtracting 1/4 from both sides gives me h squared equaling 3/4. Taking the square root of both sides, again, needing to simplify those radicals, gives me h equals the square root of 3 over the square root of 4, or just the square root of 3 over 2. So I've now figured out that I have this 30, 60, 90 triangle, and my side lengths are going to be 1, 1/2, and the square root of 3 over 2. From here, I'm going to evaluate sine of 30 degrees, cosine of 30 degrees, and tangent of 30 degrees. Well, sine of 30 degrees is opposite 1/2 divided by the hypotenuse of 1. 1/2 divided by 1 is 1/2. Again, confirming that when I take sine of an angle measurement, it gives me the height of the triangle. Cosine of 30 degrees is adjacent over hypotenuse. So in this case, we have the square root of 3 over 2 divided by 1, or the square root of 3 over 2. Again, this confirms that our cosine measurement of an angle is going to give us the horizontal distance. Last but not least, we have tangent of 30 degrees. Tangent of 30 degrees is going to be found by taking the opposite divided by the adjacent. Again, this is the same as taking sine divided by cosine. Now, note that when we do this, it is going to cause us to simplify. I'm just trying to make sure that we don't have extra distractions. So when I go to simplify this, I'm going to multiply by the reciprocal of the denominator. I'm going to do this to the top and bottom. When I do that, I get 2 over 2 times the square root of 3. This can be simplified further. 2 divided by 2 is 1. So I have 1 over the square root of 3. And as always, we need to rationalize. Multiplying by the square root of 3 on the top and bottom gives me the square root of 3 over 3. Tangent of 30 degrees will equal square root of 3 over 3. Now again, we're just getting in the habit of practicing finding those different measurements. So you might be asking, okay, Ms. Vernon, we talked about a unit circle having a radius of 1. We've now talked about our 2 special right triangles, and we've created a hypotenuse of 1. How does this all fit together? Let's take a look. So I've drawn here our first quadrant of our unit circle. I've also marked a few key spots. Now recall that if I am horizontally just coming straight across, I would be at 0 degrees. If I've rotated a quarter of a turn up, I am now at 90 degrees. What are these measurements in between? Well, these measurements are going to be connected to our special right triangles that we just created. So to begin, I'm going to use our first special right triangle, our 45, 45, 90. And basically, I'm just going to drag that one right over, and we can see that the angle at the origin is 45 degrees. So this middle mark is your 45-degree measure. And using our knowledge that our horizontal distance and our vertical distance up are cosine and sine, I can write my coordinate as square root of 2 over 2, comma, square root of 2 over 2. What these coordinates are representing is the distance from the origin to this point. Horizontally, we moved root 2 over 2. Vertically, we moved root 2 over 2. All right, let's bring in our other triangle. So in this triangle, when I slide it into place, we can see that this is marking our 30-degree measurement. At our 30-degree measurement, our coordinates are going to be the square root of 3 over 2 and 1/2. Horizontally, we went root 3 over 2, and vertically, we went 1 unit up. Now you might say, okay, Miss Vernon, great. We've come up with 2 of the 3, but where does the third one come from? Well, I'm going to do something a little tricky. I'm going to rotate my image, and then I'm going to flip it to the left. Oh, just kidding. Flip it and then rotate it. I apologize. And you'll see that this third one is simply your 60-degree angle. Now I know I inverted all of my numbers, so it looks a little funny, but we can still figure out that the coordinate here would be 1/2, comma, root 3 over 2. So now we have figured out what our unit circle will look like in quadrant 1. Recall, we also know that the coordinate at the beginning, or at 0 degrees, is 1, 0, and at 90 degrees, it will be 0, 1. So great, Ms. Vernon, we have these relationships. We see where they come from, but how are they helpful? Well, oftentimes when evaluating with our trig functions and the unit circle, these are going to be the values we calculate. So let's take a look at, well, what does that mean? How can we use the knowledge of the unit circle to evaluate different situations? So first things first, I want to remind you that the coordinate that you see is your cosine of that angle measurement and the sine of that angle measurement. Now, in this image, I have gone ahead and I added in our radian equivalent. So we have pi over 6, pi over 4, pi over 3, and up here at the top is pi over 2. You can do that using your unit conversion that we learned yesterday. But during class today, we'll actually talk about where those terms or radian measurements come from a little bit more. So now that we have that, let's start with our first problem. So in our first example here, I'm asking you to find the sine value at pi over 3. So I'm going to go ahead and look at pi over 3 radians, and sine is the y coordinate. So this at pi over 3, the sine coordinate is root 3 over 2. That means that if I typed in sine of pi over 3 on the calculator, I would get the decimal equivalent to root 3 over 2. Go ahead, try it if you don't believe me, but it does work out. When working with these core values, we're going to always expect that you get the answer exact. That means no decimals. I want to see the square root of 3 over 2. All right, let's look at the next example. In the next example, I'm asking you to tell me what is theta so that when you take cosine of it, you get root 2 over 2 out? Well, the cosine value is the first one. So I'm looking at the first value and I see that we have root 2 over 2 right here. So I would say theta is either 45 degrees, or it could also be stated as pi over 4 radians. Both of these are acceptable answers, and typically we will specify in radians or degrees when we ask you to do a problem like this. So there's your lesson explaining where the values come from on the unit circle, specifically connected to the coordinates, as well as identifying that cosine is the x coordinate and sine is the y coordinate. Check in with us for our lesson today and learn how we come up with the other 3 quadrants. We'll see you soon. Bye.